Hey, let's talk about leaderless replication. There are two implementations of leaderless replications in most databases. So the first one is the client-driven. Uh, Client writes to several replicas. So you can imagine if I had a client here and he's writing his write request as well as read request to several different replicas. If this whole cluster has three replicas, let's say all of his write and read request goes to every single node. The second implementation is a coordinator performs the write on behalf of the client. So this is called coordinator mediated. So you can imagine client here, he sends some request to a service. The service is responsible for coordinating requests, and coordinating requests will be sent down to each of the replicas. Right? And these are all replicas. Simple to understand here. Leaderless replication. Some of the most notable databases that use this replication schema is DynamoDB from AWS. DynamoDB uses uh, leaderless replication under the hood. DB, leaderless. The properties of leaderless replication. So clients, as we did mention, that they can send read and write requests directly, or the coordinator sends on their behalf. All replica can accept read and write requests. So, but we're primarily concerned with write in this property. So all replica accepts write requests from the client, and that's why we call leaderless. Right? There's no election needed to maintain consistency among the replicas. So no election, and there's no failover. So if one node fails, other replicas can still accept write request, and once the failed node comes back online, then the request then the outdated data gets updated by the other replicas. Now, the problem with leaderless, and one of the big technical challenge with leaderless databases, is that it can have stale value over time. So stale value over time. This is very important. Now we're going to discuss how we resolve this. We can resolve it through version number by sending several requests in parallel and then resolving them either manually by the clients or automatically by the database. Right, so here we have a diagram. This is from DDIA, right? DDIA design data intensive applications. So here you can see that in this diagram, so we start with user 1234, right? He sets the key, right? Set the key user 1234.picture underscore URL to this new .jpg. This request gets sent to replica 1, replica 2, and then replica 3, right? As what a leaderless cluster would do. Now, replica 3 is offline, so this request gets rejected. But the other two requests passes and it goes through, so these are okay and okay, right? Now, request 2, now client 2, sometime later, this is, let's say, t equal to 0, and then this maybe t equals to tau. So the second user comes and he tries to get the key, right? So the first one is set key, the second one is get key. It tries to get key from replica 3, 2, and 1. Now, replica 3 was offline between T0 and tau, and the request got sent at T tau, t equals to tau. So then, it gets back a stale value. Let's say version, right? So you see how the value here is me.new, and then the value here is me.old.jpg, and there's a version number attached to it, 6, while the other two is version 7 and it has the new value. So what it does is then this replica, it sees that this 3 is out of there, 6 is behind 7, so then we send a additional set value request. This can be sent from the client, right? You see how here client sends this request from here, from this point, goes up and then comes back down, and okay. So this is how conflict gets resolved, and each request has a version number attached to it. So you can see that number 7 is here, number 7 is here, and this one is number 6, right? So the client, once it gets back all 3 requests, it knows 7 is the latest, but one of the node is outdated, so it just sends a update request. Okay. So there are 2 ways to do this, as mentioned. We're doing read repair. So this is read repair. This can be done on the client. So client performs read repair. And the second one is background process to scan the differences. So imagine you have 3 clusters, you have 3 databases, replicas, and we initially had a coordinator service, right? So let's say coordinator service which passed down the requests. Now we have another service, let's just call it cleanup. Cleanup service, what it does is they'll try to detect drift from the 3 replicas and then fix the drift. So this one is automatic. And both styles are used by DynamoDB. And next we'll talk about quorum. Quorum is also a concept used in DynamoDB, and the property says that as long as the read and write, so read and write counts, so these are read and write counts. The read and write count is greater than n, so this is our total number of machines, or total number of replicas. Then we can expect an up-to-date value when reading from the cluster, right? So here we have an example, right? So let's say we have 1, 2, 3, 4, and 5 replicas where n equal to 5. Let's say if we have w set to 3 and read set to 3, right? So 3 plus 3, this is greater than 5. So we can almost guarantee that we're going to get the most updated value, because, right, if you take this example, if the client sends request to all the replicas, right, all the replicas, and 2 of them failed, so let's say 1 and 2, 1 failed, 2 failed, and this is a write request, by the way. Write request on 1 and 2 failed. 3, 4, and 5 succeeded, so this one is okay, this one is okay, and this one is okay. So we know that 3, 4, and 5 has the most updated value. Now, on the right side, so this person, second person, number 2, is writing, right? And, reading. The second person is reading. Same request that request gets sent to the cluster 1, 2, 3, and 4. 4 fails and 5 fails, so it doesn't get the latest value, right? It fails, and it goes to 1 and 2, right? Let's say 1 and 2 is success, right? On this side is success. It gets the old value. We get the old value, and we get the old value. But 3, we get the new value, right? And this we get nothing. So this is nothing, right? And if we go back, we can see that if it gets 6 and 7, right? It gets new value. What happens is that it gets 3 as the most updated value. and then it's going to see that 3 is most updated, and they're going to take this value, right, and then write the new value back to the old. So that's kind of what happens. So as long as your read and write request count is greater, read and write acknowledgement count is greater than the actual number of machines, we can always expect that there's at least one node which is most up to date. Okay, so here, this rule guarantees correctness as long as there's one overlapping node with the latest value. Okay. And this can be treated kind of as two knobs, where read and write request values are the shift knobs between latency and availability. You can think of it as, right, if we set read to n, right, to the highest possible count, right, and then write to 1. So that means one write, if it fails, can block the whole request. Right, and then here we're going to have low availability. Right. And if write is 1 and read is n, then we can have also low latency. But actually we can have both low latency and availability here. And moving into, let's say we change, instead of saying w plus n is greater, w plus r is greater than n, we move to w plus r is less than n, then we're decreasing our consistency requirements. So let's say we set our quorum to, instead of being write plus read, it has to be greater than our total number of nodes, to less than total number of nodes, then we decrease our consistency requirements, and we can potentially get outdated values. Okay. The limitation to quorum is not perfect. It still gets used by DynamoDB. DynamoDB uses this exact schema. The limitation for using quorum is that we can still have stale value over time if any of these conditions exist. So if write occurs concurrently, then we have a write conflict. It doesn't know which one came first. And it can resolve. The second one, if read and write occur concurrently. So if read and write occur concurrently, then the read can get outdated results, outdated values, right? Because it may not see the write happen before, so it could return a outdated value, or it could also return the value that write that we just set, because we don't know which one came first. We don't know if W came first or R came first. So this one is undefined read result. The third one, if write failed and not roll back quickly enough. If not roll back quickly enough, read get outdated content, outdated values. Because if client sends a read request to 3 replicas, and let's say 2 of them failed, right? And the second client sends a read request. This is W, this is W, this is W, this is R and R, right? So he writes it, but then 2 of these failed, and only one this one is success. What actually needs to happen is that the whole database needs to roll back because the value is actually not set. But because R could read this new value, so now it could return the wrong value because that wrong value needed to be rolled back. And the fourth one is the node fails and a backup comes online. It could back up it could return a old stale value. So this is kind of the 4 scenarios where we have limitations. Now to resolve these limitations, we use something called we use sloppy quorum and hinted handoff. Sloppy quorum. Let's talk about sloppy quorum. Sloppy quorum is not fully quorums are not fully fault tolerant, as discussed just now. If client can only connect to some of the nodes, should we return error for all requests if quorum is not reached? So again, right, if going back to this example here, right, if client can only connect to some of the nodes, should we return error on our request if quorum is not reached? Typically, we return the error. We return error and then we roll back. So we return error plus rollback. Again, because of the rollback process, we can still get outdated value. And the next point is, should we still accept writes and write them to some node which is not a home node? So a home node, we should probably go over this example a little bit here. In DynamoDB, nodes are actually part of a instance. So you can think of, let's say if this is one machine. The machine, the hard drive, HD, is actually divided into different drives. So these are different drives. Now each drive can be a node. So this could be node 1. This could be node 1 maybe for a client. So this could be node 1. Let's say this is some other node 3, and this one is node. And they're using virtual nodes. So these are virtual nodes. Virtual nodes are essentially used for consistent hashing, but allows better I want to say better partition, for better partitioning. So instead of repartitioning the whole machine, right, we divide the machine into these virtual nodes. And the virtual nodes contain the actual node that stores the data, right? And when we need to assign, when we need to reassign, or for example, if we expand our cluster and we need to reassign the data, that data doesn't need to be moved. We only have to reassign the we only have to assign the node to its proper virtual node. So that's what it means by home node. So each node, so data exists. I want to define this better. Data exists on a subset of nodes called home nodes. Even if client has more than the home nodes. This is a bit of a circular definition, so I want to just kind of make this more clear. Right? Let's say you have 3 nodes, 1, 2, 3. No, let's use 5. You have 5 nodes. So 1 node, 2 node, 3 node, 4 node, and 5 node. 2, 3, 4, and 5. And we have a key we have a key. Let's say key value is photo. This photo gets hashed and then gets distributed, let's say, to 2. So here, 3, and 4. So these 2, 3, and 4 are home nodes. And what I was talking about earlier here is that these nodes are actually part of a machine. Right? And the machine is partitioned to support these nodes. So node 2 could be on partition 1, and node 3 could be on partition 4, and node 5 or node 4 could be on partition 3, let's say. So that's kind of the illustration of what a home node means. So one of the problems that we need to solve is, should we still accept writes and write them to some node which is not a home node? And this is sloppy quorum. Okay. So going back to this diagram, let's say if it writes to 3 node, right? And node 2 is down. Node 3 and 4 is up. And it returns okay, okay, not okay. With sloppy quorum, let's say with sloppy quorum, instead of writing to 2, and now 2 is down, let's write to 1 instead. And when 1 comes back up online, when 2 comes back online, 1 can then replicate, or any one of these nodes can give an update to 2, right? And then we return the system back to its normal state, and the write request no longer lands on 1. Hope that makes sense here. So to recap, right, let me redraw this and just recap this whole sloppy quorum. We have node 1, node 2, node 3, node 4, node 5, and our client writes to photo, key equals to photo, and it lands on 1, lands on 2, and lands on 3. Okay. So 3 is okay, 2 is okay, but 1 fails. So what ends up happening is, okay, 1 failed, now let's write to 5. This is a scenario where if we set write to 3, right? Let's say if we set write to 4. Okay. And the write request lands on 1, 2, 3, and 4. If 1 fails, and write equals to 4, then we'll write to 5. Right. So yeah, that makes sense. Okay. And these are home nodes, so photo only exists in node 1, 2, and 3. I don't want you to be confused by what we had here earlier, where all of our requests went to every single node in this photo, right? Here it's a little different. We're assuming that these are home nodes. So home nodes, again, are nodes that contain these actual keys, whereas in the earlier diagram, it was more general. Okay. So this is sloppy quorum. And we discussed hinted handoff already. Hinted handoff is when the broken node comes back online, we then make sure that missing request gets updated. So updated, and that's hinted handoff. And this is how DynamoDB handles uses. Sloppy quorums. And sloppy quorums, the biggest advantage of sloppy quorums is that it enables high availability.